This video starts off Chapter 4, which is on Unit 2 on forces. Section 4.1 is about change in motion, and this will encompass your Practice A problems. First thing to talk about is forces. Forces describe the interaction between an object and its environment. The definition of a force is an action exerted on an object. This is pretty important, guys. It's not by, it's on an object, which may change the object's state of rest or motion, which is going to lead us into 3 of Newton's laws of motion. Was the object initially in motion? Was it initially at rest? What happened when they touched each other? And what was the outcome of them after they touched each other? The standard units that you're going to use is a capital N, which is called a Newton. It is equivalent to a kilogram times a meter per second squared. So what equation is going to give you these units? Let's work backwards here. A Newton equals a kilogram times a meter per second squared. So obviously the Newton stands for force. What is kilograms, guys? What variable will tell you kilograms? That variable would be mass. Good, good. Okay? And what variable tells you meters per second squared? Good, the acceleration. Yeah. But really, what we're going to use here is net, because you want to know the net forces. So right here is your original equation. This is the equation that you want to use to start off your problems when you are showing all work for your problems. Okay, F net equals ma net. Moving right along, how can a force cause an acceleration? So what we're looking at here is force increases the velocity of an object's motion with respect to time. So if you have an acceleration, there had to have been some type of a force applied to it. It may not be a continuously applied force, like you pushed your toy car and it went down the ramp, all right? So you're not continually pushing it. But there was that initial shove, so therefore it is accelerating, and it's slowing down due to friction, force traveling opposite direction of motion. So eventually then it does come to rest. And when it comes to rest, your velocity is 0. Guys, think about this. If your velocity is 0, what's your acceleration? Yeah, your acceleration should be 0 as well. So if you have a 0 acceleration, F equals ma, or more appropriately, F net equals ma net, and your acceleration equals 0 for that problem, what's your force? Mass times 0 equals 0 newtons. Yeah, so you have to have an acceleration, an object in motion, that's changing velocities. Let's be very specific there. It's changing velocities, either speeding up or slowing down, in order to have your F net equal to some non-zero number. Okay, so this leads to Newton's second law. Newton's second law, very basically stated, is F equals ma, whereas F stands for force in newtons, m is mass in kilograms, and a is acceleration in meters per second squared. Obviously, your masses have to be in kilograms, so that's something to look out for when you're first starting off the problems. Did they tell me grams? If they told you grams, you need to calculate how many kilograms are in those grams. So my leading question here for you is based off of the equation for Newton's second law. What is the relationship between force and acceleration when mass is constant? So let's rewrite that real quick. We have F net equals ma net, and it says when mass is constant. So that equal sign is in between them here. So therefore, what is the relationship between F net and a net? It is a direct relationship. Yeah, okay, now what if I would ask you for the graphing relationship? The graphing relationship would be simple, direct. Good, guys. Okay, moving right along then. We have contact forces versus field forces. This should make perfect sense. Contact forces, it's tangible. You can touch them, right? Whereas field forces, it's around you and you can feel the effects of, but you can't really see that force acting on you. Like there isn't an arm of gravity reaching out to grab you. There isn't a finger with an electrical shock on the end of it touching you, that kind of a thing. Okay, so, long story short, contact forces involve physical contact between two objects, such as a push or a pull. So really what we're going to look at here is like a force applied or a force of tension. Okay, force applied or a force of tension would be 2 examples of this, because you can see the ropes or the strings or the bungee cords for the force of tension. Whereas the force applied, you shoved the thing. You saw that happen. The examples of the field forces are gravitational field force, electromagnetic field force, strong nuclear and weak nuclear. The weakest out of all of these is gravitational force, ironically enough. And the strongest out of all of these is strong nuclear. So I'm just going to put a little note here that says weakest field force. You should probably write that as well. Okay, free body diagrams. We're going to denote these as FBD. So if I ask you to include an FBD, then I want you to draw a free body diagram with it. Furthermore, for chapter 4, show all work is no longer just the guess method, it is the I guess method, whereas I stands for image, which is going to be your free body diagram. So you'll need to include a free body diagram with each of your problems, especially in chapter 4. Okay, free body diagrams. These are force vectors, so they're like arrows, indicating magnitude and direction. So they're a certain length, longer than, shorter than, compared to something else, and they're going either left, right, up, or down. Only show, excuse me, only show the forces that are acting on the object, not by the object. And you want to label the types of forces, or force, that is or that are acting on the object. And you're going to do that at like the head of the arrow. F of G is going to be the gravitational force, and it is always present and acting straight down. This is terribly important. F of G is straight down, okay? F of G is straight down on every free body diagram, whereas F of N is always perpendicular to the plane. So F of N is at 90 degrees to whatever the surface is. So if you're on an incline, then your F of N is at an angle. But your F of G is still going straight down. It's not going like you know, perpendicular with the plane as an F of N would. So for example, the object, or something here I would like to add, that are acting on the object, and the object is drawn as a box. And then you have the arrows coming from it. So for instance, if we're going to look at these two right here, you're going to draw a box, and you're going to label F of N and F of G. And in this scenario, they're equal and opposite to each other, so this object's like stationary. It's not moving up in the air, nor is it moving down into the ground. Now, if your up in the air vector was longer, it'd be pulling up, right? Well, if your F of G vector was longer, it'd be pulled down. Make sense? Okay, moving right along. So here's an example of a free body diagram. This is kind of sort of what I would like you to look at. We're just going to use F of N, F applied, F of G, and F of F. Eventually you will become more specific and say Fs max, or you will say F of K, depending on which type of friction we are talking about. This is what I would like you to apply to your free body diagrams. Just a little reminder of where they are written. Okay, so with that in mind, you will find more practice here at this physicsclassroom.com page, and you'll see some similarities to it if you do this right now and then go and do your worksheet. So please make sure that you take a second and click on this link here, or type it in and try some of these problems out. The right answers are after you try the problem. It'll pop up and tell you yay or nay. Next. Sample problem A. So free body diagram. Physics textbook is at rest on a desk. Gravitational force pulls the book down. The desk exerts an upward force on the book that is equal in magnitude to the gravitational force, and then obviously opposite in direction. Draw your free body diagram in this scenario. So technically there's no givens on this one, right? It's just telling you that you have an F of N and an F of G. So my first question to you is, how are objects drawn on a free body diagram? Regardless if it's a car, a bucket, a person, whatever, a physics textbook, everything is going to be drawn as a box. Okay, so there's our physics textbook. Where does F of N go, guys? F of N is always perpendicular to the plane, right? Well, here's our plane right here. Here's our surface, here's our plane. So perpendicular to that plane would be like this. And then you're going to label F of N at the head of it. Okay, how does F of G always work? F of G is always straight down, regardless if it's on an inclined plane or not. It's always just directly straight down. So this one we will label F of G. What you need to be careful on this sample problem is that your F of N equals the same length as your F of G. So technically, if we want to talk about this, how is your f of n and f of g working, guys? Are they working horizontally or are they working vertically? They're working vertically. So would you call that f net y or f net x? This would be f net y. Well, f net would be f of n plus, remember net means sum of. Okay, so that would mean f of n plus a negative f of g. With me? Okay, because you want to take the sum of if you're taking the net of something. But you also have to take direction into consideration because these are vectors. Vector literally means magnitude and direction. So f net in the y is f of n minus f of g. So f net in the y, 0, equals f of n minus f of g. Therefore, f of g equals f of n. It's just one's like a positive 6, f of n, and the other one's a negative 6 newtons, f of g. F of n is positive because it's heading in a positive direction, up, and f of g is negative because it's in a negative direction, straight down. Okay, so we're going to stop that video right there. Please make sure you're only doing the front side of your free body diagram worksheet. We will be doing the back side in class, so if you'd like to work on it, that's great. I just really ask that you do it in pencil and not in pen, so we can correct that together. But the front side is what's mandatory, those 8 answers right there. So you should have 8 free body diagrams, 8 boxes with vectors drawn on them with labels at the end of the vectors for your practice 8 points for tomorrow.